This lecture is on multi-tenant isolation. So this is like partitioning and network virtualization in cloud data centers. So we are going to talk about three technologies actually, four here in the list, but really VXLAN, NVGRE and STT, which can all be grouped under NVO3 as those three technologies, and they are really used in the cloud data centers today. All right, and by doing this discussion, actually, by the time we come to the cloud, we would have finished all the networking, as I said before. Last tunneling protocol that we are going to talk about is STT. It's a very new one, and it is proposed by actually Nicira. Nicira is the company that was bought by VMware. So VXLAN was VMware, and VXLAN is very widely implemented. Nicira is a new startup which was bought by VMware for $1 billion. And so they had some new technology, and one of them is STT. So STT is Stateless Transport Tunneling Protocol, and it does Ethernet over TCP-like over IP tunnels. So you remember VXLAN was Ethernet over UDP over IP. There was a UDP header, right, in the middle. Here we have a header which is TCP instead of UDP, but it is not TCP. Header is TCP, but the rest of the protocol is not, so it is called TCP-like. Okay? And over IP tunnels, GRE and IPsec can be used instead of IP. So if you don't want to use IP, you can use IPsec if you want security. So, but you still have the Ethernet over TCP-like over GRE or over IPsec, whatever, right? I'm going to explain that TCP-like in great detail. So the tunnel endpoints are generally inside the end systems, which means vSwitches. And the main differentiator for this protocol from other protocols that we have talked about, like Trill, VXLAN, NVGRE, and so on and so forth, is that this is designed for large 64 kilobyte blocks. Why 64 kilobyte blocks? Because that is how much you transfer when you do any of this map reduce or anything database access nowadays. When you do data transfers from the storage, you do one chunk which is of 64 kilobyte. So it was not designed to optimize for little packets, but for really large blocks. So many other protocols use UDP, and then they disallow fragmentation. So basically what happens is your packets frames have to be very, very small, because if you don't allow fragmentation, you have to send very small packets. But with TCP-like, what that means is that you have header is identical to TCP. Header is same, but the protocol is different. So header is identical to TCP, and even the same protocol number 6. Now much of this will change, I think. Okay, this is just very beginning. You can see September 2013. And so this was proposed, actually this was proposed to IETF last year, and they have to update these drafts every 6 months until they become an RFC. So the last draft is version 4, STT 4, it says right there, 4. So fourth revision was last month, right? So this might change later on, but right now the protocol number is 6. And when in IP you have protocol number 6, that means TCP, right? And so the confusion in my mind would be that if it goes to some device, switch is one thing, but if it goes to some real VM, they will give it to TCP module, and which will be highly confused with this whole thing, right? So someday they will have a different protocol number. It's not a big deal to get a protocol number 66 or whatever number you want, right? So the protocol number right now it is 6, which is same as TCP. But the protocol is different. It does not use three-way handshake. It does not have any connections. It does not have any windows. It does not have any retransmissions. It does not have any congestion state. So everything that you use TCP for is not there. So in that sense, it is like UDP. Reliability, and that is not there.
So why is the banking?
Yeah, it is coming up in a minute. Okay. So they are using TCP header, not UDP header. They are using TCP header, but the protocol, how you handle the packet once it comes to the destination is different. And so I'm going to, there are more slides explaining that. Now, before we go to that, is that bump traffic is handled by IP multicast. So this is a standard practice. I mean, when you have to send bump over IP, you have to use IP multicast. This was done by VXLAN. This was done by NVGRE. This was done by everybody. So the reason they want to use TCP is because there are hardware devices that are being used today which implement TCP in the hardware, which do the segmentation and reassembly in the hardware. And therefore, they are arguing that we use that hardware and we can do it much faster than if we did UDP. Alright, so those devices are called LSO or LRO. LSO is large send offload. So this, if your Ethernet card supports LSO, which many Ethernet cards do, then you can give them 64 kilobyte chunk and they will break it off. Because this is a common thing they have to do every day. So that's why they have this special feature in the Ethernet cards. So LSO card will send a large chunk of data to the NIC and with the metadata which says, well, it is going to this destination, whatever else is going to go. NIC makes the MSS size segments. MSS is what? Maximum segment size. That is the TCP packet size, right? MSS size segments and adds checksum, TCP, IP, MAC headers to each segment. So all of this is done by the card, by hardware. And large receive offload. Then some cards do LRO also. So, I mean, you don't have to have both the functions in every card, but as I said, we talk about functions. LSO is one function, LRO is another function. And some cards do both, some cards do one. So the next function is large receive offload, where NIC attempts to reassemble the multiple segments and the larger chunks to the host. Host does the final reassembly with fewer per packet operation. Alright. So STT takes advantage of LSO and LRO feature if available. Using a protocol number other than 6 will not allow LSO LRO, because they bypass all the Ethernet card will bypass all other protocol types. So this is the reason they want to use TCP protocol type. Now, not only that, they have optimized it in many different ways, and they feel that this whole protocol is much less taxing on the CPU as compared to other options that we have. So because they have a large data size, per payload overhead is less. The context ID is 64-bit tunnel end identifier, endpoint identifier, EID. So each tunnel which ends here, look at these tunnels, they end at the V switch. And so this red and blue line are the tunnels. Hold on, let me correct that. Okay, let me first come back here. Optimization, 2-byte padding is added to the Ethernet frames to make its size a multiple of 32 bits. So they go to the extent of making sure that your packets are multiple of 4 bytes, 32 bits. Because when you fragment them, when you use them, when you do anything with the packets, you have to align them to 4 bytes. So you might as well align from the beginning. That is one thing. Then source port is a hash of the inner header, and this was done even in other places we seen, like we cite in VXLAN. The source port, the port number, and the layer 4 port number is a hash of the inner header. So what you do is you take this source MAC address, destination MAC address, and VLAN ID, and then hash them to get a number which is 16-bit, and use that as a port number. With that, what will happen is all the packets that belong to that source, that destination, and that VLAN will go through one path, and the other port numbers, other VLAN ID or destination or source, whatever, they will hash to a different port number. And just by looking at the port number, you can say, well, port number 5 go this way, port number 6 go that way. So you can have equal cost multipath without making anything out of order. Everything will be in order because all the packets of that particular flow are going in one path. So this allows ECMP. ECMP with each flow taking a different path and all packets of flow take one path. There is no protocol type field. So now this is another thing that I think will change. Right now there is no protocol type field. Payload is assumed to be Ethernet because they are not sending anything other than Ethernet. Well, this is today, and if the protocol stays for a long time, if it is really good, people will try to send anything through it, and so they will need a protocol type field at some point. But as it is right now, there is no protocol type field, and so there is only one payload type, which is Ethernet. Alright, the frame format. So 16-bit MSS. Since the maximum segment size in TCP is 16 bits, you cannot send any more than 2 raised to 16 bytes, which means that 64 kilobyte. So they have set it, that is the packet size. L4 offset. So this is the by the way, this is the header, and you can see that this is the STT header, which is same as, this is not the TCP header. TCP header is before STT header. So there are two headers here. There is this STT header and then there is a TCP like header. Right? So I haven't shown the TCP like header here. This is the STT header. This is like VXLAN header. VXLAN header was very simple. All it had was the VNI field. Remember that? There was a flag which was just 1-bit flag which said VNI is valid. Here, the STT header includes the version number, the flags, L4 offset, maximum segment size, priority code point, VLAN ID, context ID, and so on and so forth. So VLAN ID valid, this is just 1 bit, which says that this ID is not just a 0 or a random number, this is a valid field. And the flags are again some 1-bit things which are like checksum verified, checksum partial, IP version is V4, and TCP payload here and then reserved. Okay. So anyway, so all of this is let us just go through these fields one by one. So L4 offset. L4 offset is from the STT header to the start of payload encapsulated L4. So beyond this, in the payload you will have the Ethernet field and other things, right? So the question is, where does the payload begin? Because there is a padding and other things, right? So you can quickly find that by using this offset. Checksum verified, that means the checksum covers the entire payload and is valid. And checksum is partial. Checksum only includes the TCP IP headers, so it doesn't include other headers. And so they have two options for checksum. Destination port standard to be requested from IANA. So what that means is that most of the applications have standard ports, such as HTTP has a standard port 80. FTP has a standard port 21. STT will have a standard port someday. So what does the port do? When a packet comes to a host, it looks at the port number, and then whichever process says that I am responsible for this port number, it is given to that process. Right? FTP server says to the networking code in a host that, look, I am responsible for FTP, so anytime you get a packet from port 21, give it to me. Right? HTTP server says the same thing, says I am responsible for port 80, whenever you get a packet for port 80, give it to me. So same way here. STT code or module will reserve that code. Right now it is just not standard. Alright? And so you can use any number as long as both ends know what number to use, is fine. With the standard, actually nobody else will use that port, and so you will be better off. So source port is selected for efficient ECMP. So source port, as we said, is basically hash. ACK number. So there is a field ACK number. Okay, this is interesting. ACK number is not in the STT header. ACK number is in the. Okay, I'm sorry. There is a slight confusion here, and we switched the context, and I did not mention that. This was about the STT header. This slide is about the TCP header. So the destination port is in the TCP header, source port is in the TCP header, ACK number is in the TCP header. So the TCP, in the standard format, when you send something, you give it a sequence number. You can say this is here the segment number 513, and then there is they don't use the segment number. They say here is the byte number 513. So your segment starts from byte 513, so you put that number. And the return side, you get acknowledgement which says I got everything up to byte number 513. Okay, or 1024 or whatever number the last byte was. So that is that. This is the ACK number, which is a number which is coming from the other side, but it is not really the ACK because there is no acknowledgement. What it is they are reusing these fields for a different purpose. So the ACK number is being used for the payload sequence identifier. Same in all segments of a payload. So you have 64K byte chunks. They become lots of segments. All of those segments will have this number which will be used at the other end to assemble that back into one. Right now I am managing this cloud. I tell everybody, look, we are going to use port number 325 for STT. And that's become a standard for my data center. It's not a standard for some other data center, but it's okay for here. So in every host, 325 is for STT. It's the local standard. The destination port has to be well-known port because you are going to start the conversation. So I want to talk to you, so I have to know exactly what number to dial, which is your port number. Once I dial it, my number actually, so source port is random. Source port is always random because it doesn't matter. Once I send you a packet with source port of 33, you send it back with a destination port of 33 to me. And my network code will give it to me because it knows that 33 I used. Right? So the source port is random. The destination port has to be well known simply because we want to make sure that the right process on the destination gets it. Okay? And nobody else opens that port. Okay? So what they have done is that they have reserved, I think up to 1024 are standard. Anything over 1024 is available for grab. Anybody can use for anything over 1024. So for example, when some of you run torrent code, BitTorrent, they ask you what port number you want to use, 3456. You can use any number you want, as long as that number is registered with your router, so the router can send it to your computer, things like that. So the port number is just simply used for getting it to the right place. ACK number, sequence number. Okay, so ACK number, we now know that now ACK number is used as the payload identifier, sequence identifier. Sequence number itself, which is another number which is in the packet, is used for the length of the payload plus offset. And this is correctly handled by putting this thing over there, sequence number there, it is correctly handled by LRO devices. So there are these little hacks there, okay, which actually I think will probably go away. But right now that is what it is that sequence number is being used for the length and the ACK number is being used for the sequence number. No ACKs. So even if you are missing something, it goes. High layer TCP can handle retransmission if required. Middle boxes will need to be reprogrammed to allow STT pass through. So that's another little problem, is that firewalls may not allow certain port numbers. Right? It is not port 80. They only allow port 80. So that is one thing that you really need to make sure that your firewall allows whatever port numbers you are using. All right. So now, what this picture shows is the TCP header. The TCP header is a source port, destination port, and then it has these two fields, payload length and segment offset. They combine these two fields, 16-bit plus 16-bit, 32-bit. This becomes the sequence number. I'm sorry, this is the other way around. This is the TCP sequence number. It is divided into two 16 bits. One is the payload length, one is the segment offset. All right. This 32-bit of TCP becomes the payload sequence number. All right. The red is the standard TCP field, and this is their interpretation. Now, if this looks confusing, that's why it is worth $1.3 billion. Okay. So, no, actually they had more than this. I'm just kidding. So this is one of the things they had. And we will talk about other things later on. Okay? Now, I think you really need to read that draft which was mentioned in the first slide. And it's easy to read draft actually. It's not very difficult to read. And that's the only reference there is. All right. So, to summarize this, STT solves the problem of efficient transport of large storage blocks, and that's the differentiator. Everything else is designed for little pieces. This is designed for real traffic, according to them. The uses Ethernet over TCP like over IP tunnel. So TCP like, you understand, is that they use TCP header, but they interpret it differently, and of course they don't use the TCP protocol. And designed for software implementation in hypervisors. And it is designed for software implementation making best use of the hardware that is available today. All right. So basically, summary of this whole chapter whole module is that NVO3, Network Virtualization over Layer 3, is a generalized framework for network virtualization over L3. It covers both L3 and L2 connectivity. So you could have L3 over L3 or L2 over L3, but the underlay is L3. So we talked about three protocols: NVGRE, using GRE, VXLAN, which uses UDP over IP, and STT, which uses Ethernet over TCP like over IP. By the way, I didn't mention this word stateless. TCP is stateful. TCP is stateful. What is the state? So when you send a packet, basically it remembers what packet has come, what has not come, and then it retransmits, and all that is state in the end host, right? This is stateless in the sense that whatever comes, whatever doesn't come. It's like UDP is stateless. Okay, so in the protocol sense, STT is closer to UDP. In the header, it is closer to TCP, and therefore it is a stateless protocol. So this picture will apply to STT as well. You do exactly the same thing in all three. Whether it is NVGRE, STT or VXLAN, you have to dig tunnels between the, you have to dig the tunnels. And so the tunnels are different in three different protocols, right? And the STT's contribution, like Suvarthi said, is that the tunnels are really big enough to be taking 64 kilobyte packets. That's all that is. Okay, they're efficient for 64 kilobyte packets as opposed to VXLAN, which may not be efficient. But having said all this, VXLAN is the industry standard right now. Okay, VXLAN is implemented in every place where you go, and the others are trying to get in there. All right, I think we finished all the summary thing, and so that should be it. A reading list. Basically, I have just repeated what was there before. And yeah, so that should be it.